Okay, good morning, everybody. Uh, there is one important announcement I have to make, and I'll definitely also send it by email. But there is now a relaxed university policy on the S/U grading. So S/U means satisfactory slash unsatisfactory, and usually it takes some effort to switch to this kind of grade because typically the university wants you to get a letter grade. But because of all this coronavirus stuff, it's now automatic. So if you think you won't be satisfied with your grade, you can switch to this S/U, and then, well, unless you're doing very badly, you'll get the satisfactory grade, and nobody will know how well you actually did. So it's completely up to you. You can stay on the letter grading, or you can switch to the satisfactory slash unsatisfactory. Uh, so it's for you to choose. It's for you to decide. But if you want to switch, then you will be allowed. No questions asked. Okay, so I'm still thinking about how to run the final, not because I think I'll have some proctoring issues, but mostly because I just want to do it in some more relaxed way to mitigate um, all the damage this virus is doing. So I'll let you know as soon as possible. But so you are turning in your homework today, and as I emailed, all homeworks after that will be mostly extra credit, so you'll be able to bump your grade. I'll probably assign some mandatory problems, just like the ones that are super important, but the rest will be extra credit. Okay, so let's now start. And sorry, I want to turn the timer on. Great. So, okay, so I want to remind you this definition that the principal value of the integral, so here it is by definition equal to this limit. Now, I want to erase all this because I was in a hurry and it kind of wasn't really good that I didn't give any example. So I want to give a very important example here. An example that shows how principal value can actually make a difference. So let's compute this integral. And as you hopefully remember from Calc 2, this integral has no way to converge in the like regular sense. So this integral without the PV diverges badly because so if there are two problems with minus and plus infinity, then we should split it in two like this. And this thing is already plus infinity because x has an antiderivative and it's x squared over 2. When we plug infinity, we get infinity. So what happens with the principal value? So for the principal value, and this will be very surprising and very anti-intuitive. For the principal value, we don't split. Like we treat these two problems together, and that's very important. So we write an integral from minus r to r, and then we send r to infinity. Okay, so now there is an antiderivative. Sorry, I don't need the integral anymore. I need to write x squared over 2, plugging the limits. And then when we plug the limits, we get r squared over 2 minus r squared, minus minus r squared over 2, and that's 0. So this thing is 0, and so the limit is also 0. So despite the fact that the integral diverges, it turns out that the principal value is really well defined and there's no problem. So principal value makes more integrals convergent. On the other hand, so I'll state the fact, it's not hard to prove. We know that if the integral, whatever, I'll do from minus infinity to infinity, f of x dx, and that's a real valued integral, not a complex, converges in the calc 2 sense, then it is equal to the principal value. So if it converges nicely, then it's all the same, but if it diverges, then the principal value can actually help it to converge. Okay, so now let's do a real example. Now, here is a warning. This will be a multi-step example. So I'll try to do many examples because it gets harder. Well, already last time we had some examples, when we do we factor out, then we differentiate, then we do power series. So it only gets worse. Okay, so now step number 1 is that I want to transform it to an integral from minus infinity to plus infinity. As of now, there is no reason for that. So I cannot really explain you why, except that I know that it will work. But as of now, we keep in mind this kind of contour. And because it's minus r and r, it should be from minus infinity to infinity. So how do we do it? Well, we see that this is a even function. Okay. So that's an even function. So it's 0 at 0. Then, well, I have no idea what it does. It probably increases and then it decreases back to 0. And here it does the same. So we are computing this integral. Okay. So we know that the integral from minus infinity to 0, f of x dx, is equal to the integral from 0 to infinity of f of x dx. And this is because it's an even function, so this shaded area is equal to this area. And so this implies that if we just integrate from minus infinity to infinity f of x dx, we'll just need to double this integral. Okay, and therefore to compute this integral, we can compute this integral and then divide the answer by 2. So what we need is 1/2 times this. Now let's suddenly extend f to the complex plane. So last time I tried to show you something about sine, and sine was extended in a weird way. So instead of sine of z, we wrote e to the we wrote e to the ix. So here it will be more straightforward. That's a better example. We can realize that instead of x, we can just plug any complex number, except that this function over here, f of x, it's a really decent function because the denominator is never 0 for a real x. This function f of z is not so decent anymore because occasionally the denominator is equal to 0. Okay, and now let's draw this contour. So I want to integrate f over contour c. But I also want to index c by r. So cr is this. Finally, I'm drawing this picture in a meaningful example. Okay, so this is a circle of radius r, only above the real axis. So we go counterclockwise, and then as soon as we hit x-axis, we return to this point via this horizontal path. So CR consists of two parts, and remember that we sort of worked hard to explain why we can integrate over these not always differentiable curves. Alright, so we know that this integral over C sub r is 2 pi I times the sum of residues inside the contour. So let's count how many residues do we have. Okay, so we have residue z equal to I, and then we have several more. So we in fact need sixth root of -1. So the residues are at -1 to the power 1/6, because this is what produces the residue. Okay, so we know that -1 is e to the pi I plus 2 pi n, so -1 to the 1/6. I'll just list all the values. So pi I over 6. So pi I plus 2 pi n is 3 pi I divided by 6 will be pi I over 2, which is I. Then 5 pi I over 6. Okay, then we add okay, 4 pi n, then we add 6 pi n, so we get 7 pi I over 6. Then we add 8 pi n, so we get 9 pi I divided by, sorry, I here. Hopefully you caught this, but uh, all listed values here are correct. I was assuming I is there. Okay, so we add 8 pi I, we get 9 pi I divided by 6, we get 3 pi I over 2, have 1, 2, 3, 4, 5, I need one more. So 10 pi I, get 11 pi I over 6. So which ones are residues? Well, e to the pi I over 6 is somewhere here. Then the next one is this, the next one is this. Let's draw a picture again. So one is here, another one is here, another one is here, and then another one is here, and here, and here. So these ones are residues, and these ones are not, because they're not in the contour. So only these three friends are residues, and these are not. Okay, so now I can actually compute the residues. And now I'll go a little bit back to remind you the fact that if we have P over Q, and we know that Q has a simple zero, if Q has a simple zero, then the residue I had it earlier, hopefully. Yeah, here it is. So if we have if Q has a simple zero, then the residue is just P of z0 divided by Q prime of z0. Here it is. Okay, so what do we know? I'll actually go ahead and compute it here. Oh, and sorry, I promised that I will hold my iPad horizontally. Well, let me start now. I'll then go to the next page. Flip it. You know what? I'll start the recording because I'm afraid that YouTube won't like it. So hang on. I'll start the recording and I'll start the stream.